Welcome back to the next video, everybody. Today's video will be on some of the results from the Langlands program that we'll need to continue our discussion of Langlands tunnel. Specifically, we'll be looking at Langlands reciprocity and Langlands functoriality. References for the next few videos include Cornell, Silverman, Stevens, Chapter 6, Bushnell, Henniart, the local Langlands conjecture for GL2, and Jack A. Langlands, in addition to any other references, of course, that I give you throughout this video and the next couple of videos on this topic. Okay, what is the Weil group of a number field? First, I think you should read Tate's Number Theoretic Background. This is an excellent read. It contains a lot of information about these Weil groups. The Weil group is pretty tricky to define for global fields like this. The Weil group WF of a number field F is a topological group equipped with a continuous group HOM R from WF to the Galois group of F with dense image. If I give you a finite Galois extension E over F, I'll just define the Weil group of E to be R inverse of the Galois group of E. And then I'll define WCE to be the closure of the commutator subgroup of WE. And I'll let W of E over F be W of F mod WCE. It's easy to remember all this if you just kind of remember that there's an exact sequence from 0 to the abelianization of E, which is WE mod WCE, to W of E over F, to G of E over F to 0, where G over F is the Galois group of E over F. And of course, the natural map from the Weil group of F to the inverse limit of all the W of E over F's, where the inverse limit is over the Galois extensions E of F, is an isomorphism of topological groups, as you might have expected. Okay, what are we going to be doing? What's our roadmap? What's our strategy? First, we're going to describe local Langlands conjecture, which we'll refer to as LLC from here on out, for GLN over a local field F. When n is prime, the LLC is a theorem called the local Langlands correspondence, although I believe since Cornell, Silverman, Stevens was written, this has now been proven in generality. We don't care though. We're really going to be describing this correspondence in detail for n equals 2 because that's what we need. And we're going to apply it to both refine and generalize Theorem 3 from the previous few videos, because remember, Theorem 3 and automorphic Langlands tunnel are our two open loopholes that we need to close to finish off the chapter. Once we refine and generalize Theorem 3, we will obtain the following theorem, which we will call the global LRC, or the global Langlands reciprocity conjecture, although it's going to be a theorem for us. Let K be a number field. To each continuous irreducible representation rho from the Weil group of K to GL2 of C, there's an automorphic cuspidal representation, which we'll call pi of rho, broken down with the tensor product into local components pi sub v for every place V of K. This is a representation of GL2 of A sub K with central character det rho. And under this correspondence, pi sub b will match up with rho sub b. So what I mean by that is these pi sub b's will match up to local representations rho sub b attached to the representation rho. What are these rho sub b's, by the way? Rho sub b is a two-dimensional representation of what we call the local Weil group W sub k sub b. We often call this just the Langlands parameter of pi sub b. All right. For almost every place V, or prime V of K, if you like, rho sub V and pi sub V are unramified. And this correspondence up here, the fact that these match up under LRC, reduces easily to the familiar relation that the trace of T sub pi sub V, the Langlands class of V, is equal to the trace of rho sub V of the Frobenius set V for every prime V of K. So this is a familiar relationship we've seen in previous videos. All right. So a longer term strategy then is, once we've done this, we'll see that automorphic Langlands tunnel follows immediately from global LRC if we look at the solvable case. And so then it will remain to prove global LRC, essentially. And so what we'll do after that is we'll begin collecting the results needed to prove global LRC in the two-dimensional solvable case, because that's the only case we'll need. All right. And then we'll actually prove it, which is like a much even longer term strategy than this. So we have a little ways to go, but it sort of breaks down into two steps. See how Langlands tunnel follows from LRC, then prove LRC. All right, I'm going to give you some linear algebraic group theory so that the next slide after this makes sense. Let's let K be a field. A linear algebraic K group is just a smooth closed subgroup scheme of GLN over K for some natural number n. A group K scheme is called unipotent if it's isomorphic to a closed subgroup scheme of U sub n for some n, where U sub n is the group of upper triangular matrices, and GLN over K with diagonal entries all 1. And then very importantly, a connected linear algebraic group G over an algebraically closed field K is called reductive if its largest smooth connected unipotent normal subgroup is trivial. Okay. adjective soup. A reductive K group G is called quasi-split if it contains what we call a Borel subgroup over K. What's a Borel subgroup over K? It's a maximal Zariski closed connected solvable algebraic subgroup. Okay, so for example, like for a reductive group, just think about GLN. For a Borel subgroup within that, just think about the upper triangular matrices. It's not complicated. And then I think unipotent matrices are really easy to think about. Just think about upper triangular matrices with diagonal entries all one. I mean, obviously there are many more examples than this, but you can sort of just latch onto that one example and you'll probably be all right. If you want to read about linear algebraic groups, you can see Borel linear algebraic groups. Springer also has a book. Milne also has some notes. I like Borel the best because it's a little bit more modern than Springer, even though I learned from Springer. Okay, so why am I giving you all this linear algebraic group theory? Well, we're going to also see, kind of as an added bonus, that all of these results we've been talking about, even global LRC itself, all of these results are special cases of the following: the Langlands functoriality conjecture, which we'll call the LFC. And it says the following, and I owe you some definitions here, but we'll get to those later. Suppose G and G prime are reductive F groups, F is a field, with G prime quasi-split. And suppose I have a morphism of what we call their L groups, rho from the L group of G to the L group of G prime. That will be defined later. Then it turns out, well, under the conjecture at least, there is a corresponding map of automorphic representations. Pi to pi of rho will break pi of rho down as a tensor product of pi primes v's over places v. From G to G prime, such that for almost every v, rho sends the Langlands class at v of pi to the Langlands class at v of pi prime, which is also t sub pi sub b of rho. Okay, so I'm going to give more explanation about this conjecture in the coming videos, but for now, that's all we need. Really, I just sort of owe you an explanation of what I mean by L group here, but that bears some discussion that we're going to have to do. Okay, so we've given some references. We've set up kind of a medium and a longer term roadmap for what it is exactly that we still need to accomplish. And now we just need to accomplish it. We've also set a lot of this inside of a much larger framework, which we plan to talk about just a little bit. So I will see you next video. Thanks for watching.